In this video, we're going to investigate what it would take to launch a satellite into a low Earth orbit using a single-stage rocket. We'll base this analysis on the rocket equation that we developed earlier in this unit. So let's start with the rocket equation in the following form. Form is that the final mass over the initial mass is equal to E to the minus delta V over Vp. Let's just define those terms. So where mf is going to be the final mass of the rocket, m0 is going to be the initial mass of the rocket, delta V is our overall change in the speed of the rocket, and Vp is the speed with which we eject the propellant relative to the rocket. And just a reminder then, deriving the rocket equation, we neglected a couple of important terms, or we made a couple of important assumptions. The first was we neglected the effect of overcoming gravity, and we also neglected the effects of overcoming any aerodynamic drag. We can make a simple modification to the rocket equation to account for both of these effects. And what we do is we add a little bit of to our delta V in order to account for these effects. And what we do is we replace our delta V with an effective delta V, which we call delta V effective. So the EFF is effective. And what this means in practice is that we'd really require an effectively larger overall delta V than we'd be calculating if we're neglecting gravity and aerodynamic drag. So we increase that delta V a little bit in order to account for the effects of drag and gravity. For low Earth orbit, low Earth orbit, which is what we're going to be considering here, we call that LEO, we'll set our delta V effective to be 9.7 kilometers per second. So you remember that Earth orbital velocity for low Earth orbit is around about 8 kilometers per second. So we've increased that a little bit to account for these effects. So to do our calculations, we need to look at a rocket. So let's consider a rocket with a pretty good effective impulse, specific impulse I should say. With let's say that the ISP is 400 seconds. So that's a pretty good typical of a liquid-fueled rocket. And recall from the last video that we could write our specific impulse, ISP, in terms of the speed with which we're ejecting the propellant over the acceleration due to gravity. So that gives us that Vp is equal to G times ISP. And therefore, for a ISP of 400, our Vp would be equal to 400 times the acceleration due to gravity. And let's look at the Earth. The acceleration will take us 9.8 meters per second squared, and that gives us rounding up, around about 4,000 meters per second is the speed with which we'd be ejecting the propellant to get that specific impulse. So now we have our effective delta V, we have what our VP is, so we can say that mf over m naught is going to be equal to E to the minus delta V effective over VP, so minus 9.7 kilometers per second over 4.0 kilometers per second, and if you do that calculation, that comes out to be around about 0.09. So the mass that we could place into orbit, which is our MF, would only be 9% of the initial takeoff mass of our vehicle. So let's write that down. So I've written that down just to make the point. The thing we need to remember is that what we place into orbit is not just the payload, but also the rocket that got us up there. So all of its structure and its engines. So let's slide down our screen and note that but our initial mass is going to be equal to the mass of the payload plus the mass of the propellant plus the mass of the structure of the rocket that's holding us up there, well, that's going to take us up there. So here's our rocket. Now the top of that is going to be our payload that we're looking to place into orbit. So let's say MPL is equal to the mass of the payload. A lot of the rest of inside of the rocket was filled up with the propellant. So MP is our mass of propellant. Remember, this is at takeoff. And then the rest is everything else. We'll just call that MS, the mass of the structure. But that includes all the tanks to hold the propellant, also includes the engine and the structure of the rocket. So that's all we've got to take off. When we reach orbit, what we've finally got left is we've got our final mass, which is again our payload mass. We've now got rid of all the propellant, but we've still got the structure left. So we've got the mass of the payload plus the mass of the structure. So this is what we end up putting into orbit, and all of this has to be fit within 9% of the initial mass of the rocket. So for example, if we could get a value of the structure over the initial mass of the order of 7%, which is pretty competitive and pretty hard to do, then the mass of the payload over the mass initially would be only 2%. So let's look at what that means for some typical numbers. So if the mass of the payload that we're trying to get into orbit is, say, 5,000 kilograms, then m naught is going to be equal to 5,000 over 0.02, which is 250,000 kilograms or 250 tons. In that case, the structural mass would be 7% of the initial mass of that 250,000. So that would be 17,500 kilograms. And I'll just slide that down and say that the mass of the propellant is all the rest of the mass, so that's the initial 250 tons minus our payload of 5 tons minus our structural mass of 17.5 tons, giving us 227,500 kilograms. So in order to get 5,000 kilograms into orbit, we'd need 227,500 kilograms of propellant and a structural mass of 17.5 tons. So this shows us that it's very difficult to launch a payload into orbit around the Earth using a single stage rocket. In the next video, we're going to look at what happens if we use a two-stage rocket to try to launch into low Earth orbit.